Students, in chapter 12 thermodynamics we discuss about the heat capacity and specific heat capacity. Right? What is the heat capacity? The ratio of the heat supplied to the change in temperature is known as the heat capacity. Right? And also we discuss about that the heat capacity depends on the nature of the material of the substance and also the mass of the substance. As we consider the mass of the substance is unit, that means the 1 kg or the 1 mole. So at that time the heat capacity is known as the specific heat capacity. The definition is that the heat capacity of a substance of unit mass. The heat capacity of a substance of unit mass is known as the specific heat capacity. If the substance is gas, that means the quantity or the amount of a substance is measured in mole. At that time, the heat capacity of the 1 mole of substance is known as the molar specific heat. Again, if the substance is, or the amount of the substance or the quantity of a substance is measured in mole, like as the gaseous system, so the heat capacity of a substance of unit mole is known as the molar specific heat. On the base of this, we are going to discuss about the definition of the 1 calorie and also the mechanical equivalent of heat. And then we are going to discuss about the 2 types of the specific heat for the gaseous system. That means the specific heat at constant volume and specific heat at constant pressure. And we are going to derive the relation between these 2 specific heat, Cp and Cv. And this relation is Cp minus Cv is equal to R. This question is most important for our exam. Frequently that is asked for the 3 marks or 4 marks. Right? Obtain the relation between the 2 specific heat of a gas. Or in other words, obtain the relation or define the Cp and Cv and obtain the relation Cp minus Cv is equal to R. So first we start from what is the definition of 1 calorie. 1 calorie is the amount of heat required to increase the temperature of 1 gram of water. Old definition is that the amount of heat required to increase the temperature of 1 gram of water by 1 Kelvin or the 1 degree centigrade is known as the 1 calorie. But water is not the same amount of the heat required to increase the temperature between the 30 to 31 degrees centigrade or 10 to 11 degrees centigrade or 19 to 20 degrees centigrade. So in different gap of the temperature, the amount of the heat required is different. And due to that reason, in new definition of the calorie, here the temperature is also mentioned. From which temperature to the which temperature, the rise in temperature, the amount of the heat required, that is known as the 1 calorie. Therefore, the new definition of 1 calorie is that the amount of heat required to increase the temperature of 1 gram of water from 14.5 degrees centigrade to 15.5 degrees centigrade is called 1 calorie. Is called 1 calorie. Again, keep in mind this. Here this range of the temperature is necessary. Otherwise, your definition is wrong. Right? The amount of heat required to increase the temperature of 1 gram of water from 14.5 degrees centigrade to 15.5 degrees centigrade is known as 1 calorie. Again, we repeat the definition of 1 calorie. The amount of heat required to increase the temperature of 1 gram of water from 14.5 degrees centigrade to 15.5 degrees centigrade is known as 1 calorie. Keep in mind this word of definition, because frequently we are using the same word to define the molar specific heat and also specific heat at constant volume and also at constant pressure. Clear? Okay. Now the unit of the heat is calorie and also the joule. Right? Unit of heat is joule per calorie. How the both units are possible? For that purpose, the specific heat capacity of water is 4186 joule per kg into Kelvin. Again, the specific heat capacity of water is 4186 joule per kg into Kelvin. Means 4.186 joule per gram into Kelvin. That is in kg. That is in gram. MKS, that is in CGS value of the specific heat capacity of water. Now we know that from W is equal to JH, that is the equation suggested by the joule, how much heat is produced. So W is equal to JH, the amount of work done to produce the 1 calorie of the heat is called the mechanical equivalent of heat. In this equation, as you consider the H is equal to 1 calorie. Here the work is in joule. Here J is the constant and H is the heat energy. Generally we measure the heat in calorie. Therefore, this equation shows the relation between the two units, joule and calorie. The amount of work required to produce 1 calorie of heat is known as mechanical equivalent of heat. In this equation, we take the H is equal to 1 calorie. So in that case, the W is equal to J. J is known as the mechanical equivalent of heat, and its value is 4.19 joule per calorie. Again, the definition of the mechanical equivalent of heat is that the amount of work required to produce 1 calorie of heat is called mechanical equivalent of heat. Therefore, W is equal to J for H is equal to 1 calorie. And hence, there are two units of heat, joule and calorie. Clear this? So, only the definition of the calorie and also mechanical equivalent of the heat is important for us. Again, what is the 1 calorie definition? The amount of heat required to rise the temperature of 1 gram of water from 14.5 degrees centigrade to 15.5 degrees centigrade is known as the 1 calorie. And now the mechanical equivalent of the heat is that the work required to produce the 1 calorie of heat. The work done to produce 1 calorie of heat is known as the mechanical equivalent of heat. From this equation, W is equal to JH. And hence, the two units of heat, joule and also calorie. Clear it? Okay. Now after that, define two specific heat of gas and obtain the relation between them. Or in other words, define Cp and Cv and obtain Cp minus Cv is equal to R. This question is most important, very easy and very short answer. Okay. Now, for gas, the specific heat capacity is known as the molar specific heat. Again, for gases, the specific heat capacity is known as the molar specific heat. Why that is known as the molar specific heat? Because the quantity or the amount of a gas is measured in mole. Therefore, the specific heat capacity for the gas is known as molar specific heat capacity. Now, molar specific heat capacity are two kinds for the gases. Molar specific heat capacity are two kinds. One is the molar specific heat at constant volume, that is denoted by C suffix V. And second is the molar specific heat capacity at constant pressure, that is the Cp. Molar specific heat at constant pressure. Again, for the gas, the molar specific heats are two types. One is the molar specific heat capacity at constant volume, that is denoted by C suffix V, that means the C. And second type is the molar specific heat capacity at constant pressure, that is denoted by C suffix P, that is read as Cp. Right. First we define the both definition, or the definition of the Cv and Cp. Wording are same, only the change is this. Here volume, here the pressure. Remaining parts are same. Okay, now at constant volume, the amount of heat required to increase the temperature of 1 mole of gas from 14.5 degrees centigrade to the 15.5 degrees centigrade is known as molar specific heat at constant volume Cv. That is the same wording of definition of 1 calorie. Only this word are added. At constant volume, the amount of heat required to increase the temperature of 1 mole of gas. Earlier, in definition of the 1 calorie, that is the 1 gram of water. Here 1 mole of gas. From 14.5 degrees centigrade to 15.5 degrees centigrade is called molar specific heat capacity at constant volume. That is denoted by Cv. Clear this? Again repeat. At constant volume, the amount of heat required to increase the temperature of 1 mole of gas from 14.5 degrees centigrade to 15.5 degrees centigrade is called molar specific heat capacity at constant volume Cv. Now, as we replace the volume by pressure, so there is the definition of molar specific heat at constant pressure. Right? Again, in earlier definition of Cv, as we replace the volume by pressure. So that is the definition of molar specific heat capacity at constant pressure Cv. Now the definition is that at constant pressure, the amount of heat required to increase the temperature of 1 mole of gas from 14.5 degrees centigrade to 15.5 degrees centigrade is known as the molar specific heat at constant pressure Cp. Here, again we repeat, wording are same. At constant pressure, the amount of heat required to increase the temperature of 1 mole of gas from 14.5 degrees centigrade to 15.5 degrees centigrade is called molar specific heat capacity at constant pressure Cp. Clear? So both definitions are same, only here the difference is volume and here the pressure. And that is also said as the definition of 1 calorie. In 1 calorie, instead of the 1 mole of gas, 1 gram of water, and this at constant volume or the at constant pressure are cancelled. Clear it? So that is the definition of Cv and Cp. Now we are interested to obtain the relation between them. What is the relation between the Cp and Cv? So we know that from first law of thermodynamics, for small changes, delta Q is equal to delta W plus delta U plus delta W. Delta Q is equal to delta U plus delta W. That means whatever the amount of the heat is supplied to the gas, the sum part of the supplied heat energy is make the change in internal energy of the system, and some work done by the system. Therefore, delta U plus delta W. Now, in case of a gas, the work done is equal to P into delta V. P into delta V. Therefore, first law of thermodynamics is also written as delta Q is equal to delta U plus P delta V. Delta Q is equal to delta U plus P delta V. First, we are deriving the equation of CV, then Cp, and then we take the subtraction of Cv from Cp. For that purpose, at constant volume, if the delta Q heat supplied to the gas, if delta Q heat supplied, or the heat supplied by delta Q, then change in volume is delta V is equal to 0. Because here we supply the heat to the gaseous system at constant volume. Volume does not change. Therefore, after applying the delta Q amount of the heat, the volume change in volume delta V is equal to 0. Now, from this equation, delta Q is equal to delta U plus P delta V. Delta V becomes 0. Therefore, delta Q is equal to delta U. Delta Q is equal to only the change in internal energy of a gas system. Again, at constant volume, the heat supplied by delta Q, then the change in volume delta V is equal to 0. Because here we are discussing at constant volume. Volume does not change as we supply the more and more heat. Therefore, delta V is equal to 0. Therefore, from equation 1, delta Q is equal to delta U, because the second term becomes the 0. Okay. Now, internal energy of 1 mole of gas having the F degree of freedom. Already we derived this equation. So, internal energy is equal to half kBT into numbers of the degree of freedom into number of atom in 1 mole. Number of atom in 1 mole, like this way, the U is equal to half kBT, numbers of the degree of freedom into Na. But Na into Kb is equal to R, therefore half F R delta T. Half F R delta T. So directly we write down this equation. Again, the internal energy of 1 mole of gas is equal to the half kBT into number of degree of freedom into number of atom in 1 mole in A. But Kb into Na is equal to gas constant R. Therefore, half F R delta T. That is the internal energy of 1 mole of gas having the F degree of freedom. U is equal to F R delta T by 2. But from equation 2, internal energy is equal to supplied heat energy. Therefore, U is equal to delta Q. Delta Q is equal to F R delta T by 2. F R delta T by 2. Now, a definition of specific heat at constant volume. At constant volume, the amount of the heat required, delta Q, to increase the temperature of 1 mole of gas by 14.5 degrees centigrade to 15.5 degrees centigrade. That means the delta T is equal to 1. Delta T is equal to 1. So this amount of the heat required is known as the specific heat capacity at constant volume. According to this, Cv is equal to delta Q by delta T. As we consider delta T is equal to 1. Therefore, amount of the heat required is known as the specific heat capacity at constant volume. Right? So here we obtain the delta Q. Take the delta T this side. So delta Q upon delta T at constant volume, that is known as the C. Here we obtain the equation of the delta Q, amount of the heat supply. from using equation 2. Therefore, delta Q upon delta T is equal to Fi by 2. That is known as the specific heat capacity at constant volume. Now keep in mind that here you have some confusion about that. First we had done the equation of the internal energy. Now from equation 2, the change in the heat supply is equal to change in internal energy. Therefore, the internal energy is equal to delta Q. Here the increase in temperature is delta T. Therefore, instead of the U, I can add the delta Q. So delta Q is equal to Fr delta T by 2. From definition of specific heat capacity at constant volume CV, the amount of the heat required to increase the temperature of 1 mole of gas by 1 degree centigrade or the 1 Kelvin. So that is known as the CV, or in other words, delta T taken in this side, delta Q upon delta T. That is our CV. Therefore, CV is equal to delta U upon delta T at constant volume is equal to delta Q upon delta T at constant volume V is equal to Fr by 2. So that is the equation of the specific heat at constant volume CV. CV. There it is. Okay. Again repeat. First, from first law of thermodynamics, delta Q is equal to delta U plus delta W. But we know that the work done is equal to P into delta V. So another form of first law of thermodynamics, delta Q is equal to delta U plus P delta V. Now at constant volume, the heat supplied is delta Q and change in volume delta V is equal to 0. Therefore, P delta V 0. Therefore, delta Q is equal to delta U. Delta Q is equal to delta U. Now, internal energy of 1 mole of gas having F degree of freedom is U is equal to Fr delta T by 2. Fr delta T by 2. But from this equation, delta U is equal to delta Q. Therefore, delta Q is equal to Fr delta T by 2. Now, from definition of specific heat capacity at constant volume CV is equal to delta U upon delta T is equal to delta Q upon delta T at constant volume is equal to Fr by 2. Now, at constant pressure, delta Q heat supplied to a gas. Delta Q amount of the heat is supplied to a gas. So what's happened? Delta Q at constant pressure is equal to delta U plus P delta V from first law of thermodynamics. Here the delta Q amount of the heat is supplied at constant pressure is equal to change in internal energy of the system plus work done P into delta V. Here the volume is not constant, here the pressure is constant, therefore the volume may be changed by delta V. Therefore delta Q at constant pressure is equal to delta U plus P delta V. Now, for an ideal gas of 1 mole, from equation of state PV is equal to mu RT, but mu is equal to 1 mole, therefore PV is equal to RT. Okay. Now, left hand side P and V two physical quantity, but at P is constant. Therefore, the change occurs in only volume. Change occurs only in volume. Because at constant pressure, here the other physical quantity may be changed. That is the V. Therefore, P delta V is equal to right hand side R is the constant. Therefore, the change occurs only in temperature. Therefore, P delta V is equal to R delta T. That means the value of P delta V is equal to R delta T. Substitute in this equation. Therefore, delta Q at constant pressure is equal to delta U plus, instead of the P delta V, R delta T. dividing each term by delta T. Therefore, delta Q upon delta T at constant pressure is equal to delta U upon delta T at constant pressure plus R delta T upon delta T, delta T. Cancel only R. Now here, there is no difference between the constant pressure and constant temperature for internal energy. Because the internal energy of a system depends only on temperature. Therefore, delta U upon delta T is always Fi by 2. Delta U upon delta T at constant pressure or the constant volume both are same Fi by 2, because already we discussed about that the internal energy of a system is only depends on the temperature. Only depends on the temperature. And due to that reason, the delta U upon delta T is equal to Fi by 2. Now, delta Q upon delta T at constant pressure, from definition of heat capacity, specific heat capacity at constant pressure, so that is the Cp. Therefore, Cp is equal to delta U upon delta T at constant pressure or the constant volume plus R. But from equation 3, that is the Fi by 2 plus this R. So that is the equation of the specific heat capacity at constant pressure. Again, at constant pressure, delta Q heat supplied to a gas. So from equation of first law of thermodynamics, delta Q at constant pressure is equal to delta U plus P delta V. Right? That is equation 4. Now, the equation of state point ideal gas, PV is equal to mu RT, but mu is equal to 1 mole, therefore PV is equal to RT. In this equation, left hand side the two physical quantity, pressure and volume. But the pressure is constant, therefore the change occurs only in volume of a gas. Therefore P delta V is equal to R into delta T. Substitute here, instead of the P delta V, R delta T. Therefore, the amount of the heat supplied to a gas at constant pressure is equal to delta U plus R delta T, dividing each term by delta T. Therefore, delta Q upon delta T at constant pressure is equal to delta U upon delta T at constant pressure plus R delta T upon delta T, delta T. Cancel only R. Now, internal energy of a gas system only depends on temperature. That is not depends on volume and pressure. Therefore, delta U upon delta T at constant pressure is same as the delta U upon delta T at constant volume is equal to Fi by 2. Here we substitute this value. And from definition of the specific heat capacity at constant pressure, delta Q upon delta T is Cp. Therefore, Cp is equal to Fi by 2 plus R. Now, subtract equation 3, Cv is equal to Fi by 2 from equation 5. Therefore, Cp minus Cv is equal to value of Cp, Fi by 2 plus R minus value of Cv, Fi by 2. So that is cancelled. Therefore, Cp minus Cv is equal to R. We are subtracting equation 3, Cv from Cp. Substitute the value, we obtain the R. Therefore, Cp minus Cv is equal to R. Is the relation between the two specific heat capacity at constant pressure and constant volume. Here is